Right now, two machines built almost 50 years ago are floating in a place no human hand has ever touched. They are farther from home than anything else we have ever made, and they are still talking to us. When Voyager 1 crossed the edge of our solar system, its sensors picked up something nobody expected: the empty space beyond. The sun's protective bubble wasn't emptier than the space inside it. It was thicker. The particles floating around the spacecraft were more crowded out there than scientists had predicted. 6 years later, its twin, Voyager 2, flew through the same boundary and found the exact same thing. That single reading rewrote what we thought we knew about where our solar system ends and the rest of the galaxy begins. But here's the part that still stops me every time I think about it. These two machines were built in the 1970s. They carry less computing power than a musical greeting card. Right now, one of them is more than 25 billion kilometers from Earth. And somehow, a signal weaker than almost anything we can measure is still crossing that distance, still landing in giant dishes on Earth, still being decoded into real data. How is that even possible? Stick with me, because the answer involves a coincidence that happens once every 176 years, a slingshot made of pure gravity, and a listening system so sensitive it can hear a whisper from the edge of the solar system while filtering out the roar of an entire planet. If you're new here, hit subscribe, because we're about to take apart one of the greatest engineering stories humanity has ever pulled off. The whole mission started with a coincidence that almost never happens. In the mid-1960s, a graduate student working at NASA's Jet Propulsion Laboratory was mapping out orbital paths for fun, and he noticed something strange in the numbers. In the late 1970s, the four giant planets of our solar system, Jupiter, Saturn, Uranus, and Neptune, were all going to line up on the same side of the Sun? Not roughly, precisely enough to matter. Every planet moves around the Sun at its own speed, so in alignment, this convenient only happens once every 176 years. Miss this window? Here's why that alignment mattered so much. In space, you can't just point a rocket at a planet and fly straight to it the way you'd drive to a destination on a map. Everything out there, including the spacecraft itself, is caught in the pull of gravity, moving in curves, not straight lines. Reaching a faraway planet on a direct path takes an enormous amount of fuel, because you're constantly fighting to bend your trajectory. With the rocket engines available in the 1970s, a straight shot to Neptune alone would have taken about 30 years, if it was even possible at all. The planetary alignment changed the math completely. If a spacecraft flew close enough to Jupiter, it could use the planet's gravity like a slingshot. As Jupiter moves along its own orbit, its gravitational pull grabs a passing spacecraft, drags it along for a portion of the... NASA decided not to risk everything on a single machine. Space missions fail for 100 small reasons: a stuck valve, a software glitch, a single component that wasn't tested for the cold it would actually face. So the agency built two nearly identical probes, each with backup systems for almost everything. Spare thrusters, backup computers, two separate ways of talking to Earth. If one machine failed at any point along the journey, the other could, in theory, still carry the mission forward. Voyager 2 actually launched first in August of 1977 on a longer, slower route designed to eventually pass all four giant planets. Voyager 1 followed about 2 weeks later, but on a faster, more direct path aimed specifically at Jupiter and Saturn. Because it was moving quicker, Voyager 1 actually overtook its twin before either one reached Jupiter, meaning the probe with the higher number technically launched after what both spacecraft sent back changed astronomy overnight. Scientists half expected Jupiter to look like a giant dead ball of gas. Instead, Voyager 1's cameras captured a planet that was violently alive. When those images were strung together into a moving sequence back on Earth, researchers watched Jupiter's atmosphere twist and churn in real time, storms the size of entire planets rolling through bands of orange and white cloud. Even more surprising was what Voyager found on Io, one of Jupiter's moons. Instead of a dead, cratered rock, Io turned out to have active volcanoes, spewing blue-tinted plumes of material straight into space. It was the first time humans had ever directly seen volcanic activity happening on another world besides Earth. The discovery almost didn't happen. It rising off the edge of the moon, and initially assumed it was a background star that had somehow drifted into the frame. It wasn't. It was a plume of material shooting hundreds of kilometers above Io's surface. Within days, scientists confirmed Io was the most volcanically active body anywhere in the solar system. More active than Earth itself, driven not by anything happening inside Io alone, but by the constant gravitational tug-of-war between Io, Jupiter, and Jupiter's other large moons, a process called tidal heating that nobody had directly observed in action before. Then came Saturn, and this is where the two spacecraft's paths split apart on purpose. Voyager 1 had one very specific job left: fly close to Titan, Saturn's largest moon and the only moon in the solar system known to have a thick atmosphere. The problem was that swinging in close to Titan meant Titan's gravity would yank Voyager 1 up and out of the flat plane where all the planets orbit, throwing it on a path that would never again come close to another world. Mission planners accepted that trade. Voyager 2, on the other hand, stayed on the flat plane and kept going, becoming the only spacecraft in history to fly past both Uranus and Neptune. At Uranus, Voyager 2 found something genuinely bizarre. Every planet has a magnetic field generated deep inside it, and on most planets, that field lines up reasonably well with the planet's spin. Earth's magnetic field, for comparison, is tilted only about 11 degrees off from our actual axis of rotation, and it's centered close to the planet's core. Uranus broke that pattern completely. Its magnetic field is tilted nearly 59 degrees away from its spin axis, and the center of that field isn't even close to the planet's core. It's offset to one side. Because of this strange geometry, as Uranus rotates, its entire magnetic shield doesn't just spin evenly, it wobbles and swings through space in an unpredictable-looking pattern that scientists still study today. Adding to the strangeness, Uranus itself spins almost completely on its side, tilted more than 90 degrees relative to its orbit, so combined with its tilted off-center magnetic field, the planet behaves less like a spinning top and more like a spinning top that's also being wobbled by an invisible hand. A combination scientists still don't have a complete explanation for. Voyager 2's final planetary stop was Neptune, and it clocked the strongest winds ever recorded anywhere in the solar system, gusts reaching roughly 2,400 kilometers an hour. To put that in perspective, if wind speeds like that hit Earth's surface, we wouldn't be talking about a strong hurricane. We'd need an entirely new category, because winds at that speed wouldn't just damage buildings, they would flatten entire neighborhoods. What made this discovery even stranger is that Neptune sits so far from the sun that it receives barely any warmth at all, roughly 1,000th of the sunlight Earth gets. Yet somehow it generates the fastest winds anywhere in the solar system, faster even than Jupiter or Saturn, which sit much closer to the sun and absorb far more solar energy. Scientists still don't fully agree on where Neptune finds the energy to power storms that violent from so far out in the cold. After Neptune, there was nothing left to photograph. Voyager 2's cameras were switched off. Voyager 1's cameras stayed on a little longer, long enough to capture the iconic pale blue dot photograph in 1990, a single pixel of light that was Earth, seen from roughly 6 billion kilometers away. After that image, Voyager 1's cameras were shut down too. From that point forward, both spacecraft stopped being cameras and became something else entirely. Roving physics labs, using their remaining instruments to measure particles, magnetic fields, and plasma. In a part of space no human instrument had ever reached before. And that brings us to the real mystery of this story. The cameras have been off for over 3 decades. There's nothing left to see. So why do we still care what these two machines are doing? Because even now, in 2026, they are still collecting information that literally nothing else in existence can gather, and they're still sending it home. That raises the question I can't shake. How does a 50-year-old transmitter running on a trickle of power still manage to reach Earth from a distance that light itself takes more than a full day to cross? Start with the hardware. Each Voyager spacecraft runs on a set of onboard computers with a combined memory of about 68 kilobytes. That is a smaller amount of memory than what's packed into a basic electronic car key today. Data gets recorded onto an old-fashioned digital tape recorder, similar in concept to a cassette tape, because solid-state memory as we know it today didn't exist yet in a space-ready form. Every phone in your pocket has more raw computing power than the Voyager's entire control system combined. Now think about the radio. Each spacecraft transmits its data back to Earth using a transmitter with roughly the same power. Output is the light bulb inside a refrigerator, somewhere around 20 watts. Voyager 1 is now more than 25 billion kilometers from Earth. At the speed of light, the fastest anything can travel in this universe, a signal from that distance takes over a full day, roughly 23 hours, just to arrive. Across that entire journey, the radio wave doesn't stay in a tight little beam. It spreads out the way a ripple spreads across the surface of a pond, growing weaker and weaker the farther it travels. By the time that signal actually reaches an antenna on Earth, its strength has dropped to a fraction of a watt, a number so small it's genuinely difficult to describe in everyday terms. It's a whisper from across the galaxy's own backyard, and without an extraordinary amount of engineering on our end, it would vanish completely into background static. So how do we actually catch it? The answer sits right here on Earth in the form of NASA's Deep Space Network. 3 separate facilities built with giant 70-meter radio dishes, spread across the deserts of California, Spain, and Australia. Placing them roughly a third of the planet apart means that as Earth rotates, at least one of those dishes always has a clear line of sight to the Voyager spacecraft, No, matter what time it is anywhere on Earth. Each of these massive dishes gathers radio waves across a huge surface area and focuses them down to a single receiving point. The same basic idea as a satellite dish, just built on a much larger scale. Each dish weighs thousands of tons and can be steered with a precision that would be like aiming at a coin from across a city, except the target in this case is over 25 billion kilometers away and moving. But a dish that big doesn't just pick up Voyager. It picks up everything. Signals from distant galaxies, radio noise bouncing around Earth's own atmosphere, and static generated by the receiving equipment itself. Pulling one specific, incredibly faint signal out of all that noise takes a layered filtering process. First, engineers have to block out interference from Earth itself, things like solar towers, radar systems, and other satellites. That's part of why the Deep Space Network stations sit out in remote deserts, far from cities, operating on radio frequencies that are legally reserved just for deep space communication. Second, they filter out noise coming from the rest of the universe. Because the 70-meter dishes are extremely directional, they can be aimed at a tiny, precisely calculated patch of sky and essentially ignore everything else. On top of that, engineers already know roughly what frequency Voyager should be broadcasting on, but because the spacecraft is moving away from Earth at tremendous speed, that frequency gets stretched, the same way an ambulance siren sounds lower in pitch as it drives away from you than it did while approaching. This is the Doppler effect in action. The same basic physics used every day in police radar guns and weather radar, just applied here at a scale of billions of kilometers instead of a few hundred meters. NASA systems calculate exactly how much that frequency has shifted in real time and tune the receivers to match it precisely, which helps strip away even more background noise that doesn't match. There's a third problem, though, and it's a strange one. The receiving equipment itself generates noise just from being warm. Electrons moving randomly inside the metal components of the receiver create a faint hiss of thermal noise. And left alone, that hiss would be loud enough to bury Voyager's already tiny signal completely. The solution is almost as extreme as the problem.